Hello everybody, we shall discuss about vapor pressure. Now, you must be familiar with the term evaporation. That is a phenomenon wherein liquid phase gets transformed to gaseous phase, or liquids gets transformed to gases. That is evaporation. Now, we know that all liquids do not undergo evaporation in the same rate. Some liquids evaporate very quickly, some liquids evaporate very slowly. So that depends upon the rate of evaporation, depends upon the nature of the liquid, the surface area of the liquid surface, the temperature. These are other factors apart from the nature of the liquid. And one of the factors which decides, one of the factors in the nature of liquid which decides the rate of evaporation is vapor pressure. Now let's see what it is. Now in the vapor pressure, if you take a vessel containing an open container containing liquid in it, you have these blue balls represent liquid molecules. Okay, and the vessel is open. Now you can see there are surface molecules and there are molecules inside also. Now what happens is slowly, gradually, the surface molecules try to escape out of the liquid phase and they move on to the gaseous phase. These gray balls indicate gaseous phase. Alright, and as they move on to gaseous, gets changed to gas or gaseous phase, what happens? Some of the molecules will escape out of the vessel. Since the vessel is open system, an open vessel, the gas molecules, the molecules in the gaseous phase will escape out of the vessel. And slowly, what happens? The liquid in the vessel gets completely evaporated. That's what we see when we keep an open vessel containing water for some time. The water would have disappeared. Now, this is not the case when you close the container. When you close the container, what happens? The molecules, the liquid molecules which has escaped to the gaseous phase are trapped inside the liquid, isn't it? So the evaporation has happened, but the liquid is not able to escape out. Now, once the molecules gets evaporated and goes to gaseous phase, the space over here also gets filled with what? Gaseous molecules. Now, what happens now is that there will be energy transfer between these molecules because these molecules will also collide. The molecules in the gas phase also will be colliding with each other. And some of the energy from one molecule will be transferred to the other. Now, some of these molecules which has lost their energy, whose energy has been lowered, will come down to liquid phase. That is called condensation. Liquid, when there is conversion from gas to liquid, we say it is condensation. Finally, when an equilibrium is attained, wherein for every molecule which comes down to the liquid phase, one molecule from the liquid goes to the gaseous phase. That is, the number of molecule which is evaporating and the number of molecule which is condensing becomes equal. The equilibrium exists. Now, at this stage, when the equilibrium exists, the rate of condensation will be equal to the rate of evaporation. And what happens? These molecules in the gaseous phase will exert a pressure on the liquid surface. Okay, the molecules in the gaseous phase. Remember, the system is closed. The molecules in the gaseous phase will exert a pressure on the liquid surface. This pressure exerted by the gas molecules on the liquid surface is called the vapor pressure of that liquid. Okay, so you can say that the vapor pressure is the pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature. And the value of vapor pressure depends upon the nature of the liquid, particularly intermolecular forces, which we'll be discussing in this video, and also the temperature. These are the two main factors which decides the vapor pressure of a liquid. And remember, every liquid will be having its own vapor pressure. And the vapor pressure is designated as P0 solvent or P0 A. If you are designating or representing solvent as A, we put it as P0 A. Okay, that is the vapor pressure of the pure solvent or the pure liquid. Now let us go on to see how the intermolecular forces decide the vapor pressure of a liquid, or what is the relation between the vapor pressure and intermolecular forces. Now, you would have seen that, we have said that certain molecules evaporate very quickly, certain liquids evaporate slowly. Say, for example, you take your petrol, say equal one, say 1 liter of petrol and 1 liter of water, and keep it open. The petrol will be evaporated easily, water will remain there. The evaporation of water will be slow. You take ether and water, okay, or alcohol and water. Okay, so there the main difference there is, one of the factors which differentiates water and alcohol or water and petrol is that the intermolecular forces of water and of alcohol is different. Now, if the intermolecular force of between the molecules in a particular liquid is weak, the vapor pressure will be high, because when the intermolecular force is weak, molecules will not hold each other in the liquid phase. The molecule will allow the liquids to move on to gaseous phase. Okay, so if we go back to this video, this slide, you can see here, these molecules which are escaping out, the rate of escaping of the molecules can be slowed down if the molecules inside the liquid pulls them towards themselves, pulls each molecule towards themselves. That is, they have strong intermolecular force of attraction. If the intermolecular force of attraction is very less, what happens? Molecules will escape easily. Now that is what we see here. If the intermolecular force between molecules are weak, the vapor pressure will be high because more molecules will be present in the gaseous phase. And if it is strong, if the intermolecular force of attraction is strong between the molecule, the vapor pressure will be low. Okay, not many molecules will reach in the vapor phase, so the pressure exerted by the molecules on the liquid surface will be less, and hence vapor pressure will be low. Now, when the vapor pressure of the liquid reaches becomes equal to the atmospheric pressure, we call it as the boiling point. Now here we have the explanation for the dependence of intermolecular force with vapor pressure. Substance with weaker intermolecular force will allow more molecules to escape into the gaseous phase. They will be having higher vapor pressure. And those with low intermolecular phase will be having lower vapor pressure because less amount of molecules will be present in the vapor phase. And if we take the example of water, ethanol, diethyl ether, the intermolecular force in water is high. There will be hydrogen bonding. Then ethanol a bit lesser and diethyl ether is little lesser. So this is the decreasing order of intermolecular force of attraction. And hence, since the intermolecular force of attraction in water is high, we must say that water will be having lower vapor pressure. So when we arrange them according to vapor pressure, water will be having lower vapor pressure, followed by ethanol, followed by diethyl ether. Alright, so what we can say is those molecules, those liquids which has got higher intermolecular force of attraction will be having lower vapor pressure. Alright, now let us see what is the relation between vapor pressure and temperature. Now, the vapor pressure for a liquid at constant temperature will be constant. It will remain constant. You keep the temperature constant, the vapor pressure will be constant. But when you increase the temperature, the vapor pressure of the liquid also will increase. Now, why is that so? When you increase the temperature, what happens? The molecules gain more kinetic energy and then they will escape to vapor phase. You know that when you heat water, it will evaporate faster. Now, when the vapor pressure becomes equal to the atmospheric pressure, that temperature is called the boiling point of the liquid. The temperature at which vapor pressure of the liquid becomes equal to atmospheric pressure is called the boiling point. It is at that particular temperature that the liquid starts boiling. Now, when you plot a graph of vapor pressure versus temperature, this I have got from my chemistry blog, you can see here the diethyl ether, ethanol and water. See here on top there is here they have marked 760, that is the atmospheric pressure. Okay, diethyl ether 34.5 degrees centigrade, it evaporates faster. It reaches the atmospheric, the vapor pressure becomes equal to the atmospheric pressure at, say, you can say at around 25 or 30 degrees centigrade. So it boils faster. And when you take it at ethanol at 78.5 degree, it reaches the vapor pressure of ethanol becomes equal to that of atmospheric pressure. And it is at 100 degrees centigrade that the vapor pressure of water becomes equal to the atmospheric pressure. And it is at 100 degrees centigrade that water starts boiling. So when the vapor pressure becomes equal to the atmospheric pressure, the liquid starts boiling. Now you can see here these graphs are they're not straight line graph, they are non-linear. All right, and one more thing, when the liquid starts boiling, that is the temperature at which the vapor pressure of a liquid become equal to 1 bar pressure, when the atmospheric pressure is taken in terms of 1 bar, then we call it as standard boiling point. And the other one, 1 atmosphere, we call it as normal boiling point. 760 torr is equal to 1 atmosphere or 1 bar. And the boiling point of a liquid increases with increase in atmospheric pressure and decreases with decrease in atmospheric pressure. That is, at higher altitude where pressure is low, the liquid boil at a temperature lower than their normal boiling point because the atmospheric pressure is low. So you need not heat more to attain equivalency with atmospheric pressure. So that's why in hilly areas, the liquids, pressure cookers are used for cooking because it will not attain the 100 degrees centigrade temperature. The temperature at which water boils will be at a lower temperature. Cooking becomes difficult. That's why we have to use pressure cookers at higher altitude. Their pressure will be low. All right. So this is about this is how the vapor pressure is related to temperature. So when you plot a graph of vapor pressure versus temperature, you get a non-linear graph. Now when this was analyzed, there came an equation, Clapeyron-Claisius equation. The Clapeyron-Claisius equation gives a quantitative relation between vapor pressure of a liquid and the temperature. Now this is the Clapeyron-Claisius equation, ln P equal to minus delta H vaporization by RT plus C, where delta H vaporization is the enthalpy of vaporization. And you may be knowing what is enthalpy of vaporization. It is the enthalpy change accompanying the vaporization of 1 mole of the liquid in joules per mole. Now the unit of delta H vaporization is joules per mole. R is the universal gas constant, 8.314 joules per Kelvin per mole, and T is temperature at Kelvin scale, and C is a constant. Now, when you plot when you take a plot or draw a plot of ln P versus 1 by T, you get a straight line with negative slope. Okay, this is for water. The second line is for diethyl ether. Now, you get a negative slope. The slope is nothing but minus delta H vaporization by R. So if you measure the vapor pressure of a liquid at different temperatures, you can determine the enthalpy of vaporization. Now when you integrate this equation, you get the integrated form of Clapeyron-Clapeyron's equation is ln P1 by P2 equal to minus delta H vaporization by R 1 by T1 minus 1 by T2. You can take the reciprocal of this, you can put it as ln P2 by P1, then this negative sign will be lost. Okay, some text showed like that, ln P2 by P1 equal to plus delta H vaporization. Alright, when you take logarithm, what happens? A 2.303 will be added here in the denominator on the right hand side. Okay, so P1 and P2 are the vapor pressures at temperatures at T1 and T2 respectively. So using this equation, vapor pressure of the liquid at another temperature can be calculated. So this equation, or Clapeyron-Clapeyron's equation, gives us the relation between, a quantitative relation between vapor pressure and temperature. There are a lot of problems associated with this equation and vapor pressure and temperature. If you refer books, you will get a lot of problems. Try to solve those problems, which involves use of Clapeyron-Clapeyron's equation. So we have seen how the vapor pressure is related to the intermolecular force of attraction for a liquid and also the temperature of the liquid. Thank you.